This is Dr. Vermilio. In this lecture, we'll review physiological measurements. Physiological measures include tympanometry, acoustic reflexes, otoacoustic emissions, and the auditory brainstem response. No behavioral responses are required for these physiological measurements. In other words, we're not going to have the patient or the client respond to the sound, to the presentation of sound. All they have to do is just either sit there. On some of the tests, they're actually encouraged to go to sleep. These physiological tests, are not hearing tests. They are measures of the functionality of portions of the auditory system. Emittance audiometry includes tympanometry and acoustic reflexes. The auditory evoked responses includes otoacoustic emissions and ABR. Emittance equals impedance plus admittance. Impedance is opposition to energy flow. Admittance is the flow of energy. Commit this last bullet point to memory. Admittance is the flow of energy. And in our case, we're going to talk about the energy from sound, okay? So admittance is the flow of energy. Today's emittance instruments are designed to measure the admittance characteristics of the outer and middle ears, known by these names. Excuse me, an emittance instrument, an admittance instrument, or a middle ear analyzer. All three of these instruments represent the same thing. It might also be called an impedance bridge. That's an old name for it. A probed tone is presented at 85 dB SPL, usually at 226 hertz. So for emittance measures, picture a little plug going into the ear, and it's delivering the sound called a probe tone. And it's usually at about 85 dB SPL and 226 hertz. An automatic gain control is used to keep and maintain the probe tone levels. So if for some reason the level of the probe tone in the ear changes, if it goes down to say 80 dB, then there's also a microphone in the probe that will measure the sound pressure level. If it's below 85, then the amplifier will kick in and the voltage will go up, and the equipment will bring the probe tone back up to 85. Emittance measurements are inferred from level measurements of the probe tone as the air pressure in the ear canal is changed from positive to negative. So we're doing a bunch of things here all at the same time. We're playing a probe tone in the patient's ear. We're measuring the level of the probe tone, so there has to be a microphone. And then we're going to change the air pressure in the ear canal. We're actually going to force air into the ear canal, and we're going to take air out of the ear canal. We're actually going to change the pressure from a positive air pressure to a negative air pressure. And we're going to answer the question, how does the level of the probe tone change as we push air in and take air out of the ear canal? In the clinical application of impedance measures, we do not measure the integrity of the middle ear structures directly, only the efficiency with which a low-frequency probe tone is transmitted. Don't forget, admittance is the flow of energy. It's actually the flow of sound energy into the middle ear. For example, admittance. Let's discuss admittance. For example, move your arm side to side while standing up. Next, move your arm from side to side with it submerged in water. All of a sudden, it's much more difficult to swing your arm back and forth. Okay? So there's an increase in the resistance to the flow of your arm, or the motion of your arm. There is greater resistance to the flow of energy while submerged in water. In other words, there is greater admittance or flow of energy when moving your arm in the air. There's less admittance when we move our arm back and forth submerged in the water. So that's what we mean. That's an example of the flow of energy changing. Tympanometry is a measure of the change in admittance as air pressure changes. As the cavity size increases, so if we measured the size of the external ear canal, as the cavity size increases, the admittance of an acoustic system increases. In other words, as the ear canal volume increases, admittance, or the flow of energy into the middle ear, increases. Tympanometry provides a means of separating the admittance due to the ear canal from the admittance due to the middle ear. So here's a little guy waiting for the measurement of his tympanogram. So we're going to conduct tympanometry. Notice there's a little probe tip that goes inside the ear, and we're going to force air in and out of his little ear. Because of that, we need to get a very, very good seal with that rubber probe tip seated inside the ear canal. This is probably at the beginning of the test. I don't know if he's going to like what happens next, but hopefully he did okay. Okay, tympanometry. First, we're going to push air inside the ear canal so we have a positive air pressure. And the nomenclature that we're going to use, or the unit of measure rather, is decapascals, D-A-P-A. And we're going to force in air pressure up to 200 decapascals, which effectively reduces the motion of the tympanic membrane put into the ear. So imagine the ear canal, imagine a plug placed in the ear canal, air is forced into the ear canal. You're looking at the tympanic membrane, and all of a sudden it starts to stiffen up because we're forcing all this air into the ear canal. The admittance at 200 decapascals is going to be relatively low. It's a reflection of the admittance of the ear canal only, since the tympanic membrane isn't moving. Okay? The air pressure is then changed from 200 to 400 decapascals. You know what, let me back up a little bit. So the admittance goes to, or rather the pressure goes to 200 decapascals. We're forcing all this air in the canal. When we do that, the sound from the probe tone bounces off this very stiff tympanic membrane. And when the microphone measures the sound pressure level, we find that the 85 dBA probe tone will actually increase in level. When we see an increase in level of the probe tone, then we're going to infer that we have a decreased flow of energy going into the middle ear. So that means that since the eardrum is so stiff, it's not vibrating as well as it normally would under normal conditions. That means that the probe tone is being reflected back. So there's an elevation in probe tone. The equipment will measure this, will detect this increase in probe tone level. The automatic gain control kicks in, decreases the voltage to the speaker. Now the probe tone goes back down to about 85 dB SPL. And from that little measurement, we're going to infer the flow of energy going into the middle ear. So as the probe tone level goes up, we're inferring that the admittance, or the flow of energy excuse me, into the middle ear decreased. The pressure is changed from 200 to minus 400 decapascals. For a normally functioning middle ear, there should be maximum admittance, or flow of energy, at approximately 0 decapascals. And that's the same pressure as the atmosphere. Wherever you are, in the mountains, on a plain, in a valley, at sea level, 0 decapascals will represent the air pressure, the same air pressure as the atmosphere. This occurs when the pressure in the middle ear is the same as the atmospheric pressure in the ear canal. When this happens, the TM should vibrate most efficiently in a healthy auditory system. So here's a picture of our tympanogram. The x-axis represents the pressure, air pressure in decapascals. 0 decapascals represents atmospheric pressure. meaning that the air pressure inside the middle ear, behind the eardrum, is the same as it is in the ear canal. This represents positive ear pressure. So this is when we're taking the patient through the test and we're forcing air inside the ear canal. And then we start to take the air pressure out, so we start to take the air out. Now we're at 0 decapascals, same pressure in the ear canal as the atmosphere. And then we start to go into negative pressure. So we're actually, the probe now is going to act sort of like a vacuum. It's actually going to draw the air molecules out of the middle ear. Excuse me. And we'll go into, excuse me, we can go up to minus 400 decapascals. The y-axis represents admittance, or the flow of energy into the middle ear. That's measured in millimoles, or an equivalent volume in milliliters. So we're going to plot how admittance, or the flow of energy, changes as a function of the pressure. So as pressure changes, admittance will change in a healthy ear, and that's what we're going to measure. Know that a low admittance means that there's very low energy going into the middle ear. High admittance means that there's more energy going into the middle ear. Okay, and here's a tympanogram, very, very typical of what we can see. So we start with the probe in the ear. We push in some air pressure up to 200 decapascals, and we see that admittance is at this point. So this is the flow of energy. This also represents admittance related to the ear canal only, because we're stiffening up the middle ear. So we don't see how the does not represent the admittance when conditions are normal, or when the pressure is at 0 decapascals. All right, so the patient, actually what occurs is the patient has the plug in the ear. There's no pressure put in the ear. They hear this 226 hertz probe tone. All of a sudden, air pressure is forced into the ear canal, and in a healthy ear, the patient will hear this. All of a sudden, the tone becomes muted. The tone becomes muted because all of a sudden we have less admittance when we force air pressure in the ear canal. The eardrum is now stiff. When it's stiff, the transmission of sound from the ear canal to the middle ear, to inside the middle ear, decreases. So the flow of energy actually decreased when we pushed all that air inside the ear canal. So admittance is over here. As the pressure changes, then the probe tone will actually increase in level to the patient. So the patient hears this probe tone increase in level, but the microphone in the probe in the ear canal detects that the level of the tone is decreasing. Okay? So the level of the tone is decreasing in the ear canal. The level of the tone, if the patient can hear it, increases to the patient until we reach around 0 decapascals, which is atmospheric pressure. Now we take air pressure out of the ear. Basically, the air is being sucked out of the ear canal, and now we're going back to a stiff phase of the eardrum. And as we do that, admittance is going down while the level of the probe tone is going up in the ear canal. That's what the microphone's measuring, and the level of the probe tone is actually decreasing again to the patient. So the patient can hear the probe tone. What they'll hear is a decrease in the level. So the patient hears a decrease in level. The microphone is reading an increase in level in the ear canal. And we're going to infer from an increased probe tone level that admittance is decreasing. Okay, so that's how the whole thing relates. This is also called the tympanometric peak pressure right here. So that's the pressure for the peak of the tympanogram. Okay. This is admittance of the middle ear, or it's also called YTM, so the difference between this point and that point. Well, let's see, and this is everything I just said. Admittance is inferred from the level of the probe tone. Low admittance is inferred from a higher level of the probe tone. and high admittance is inferred from a lower level of the probe tone measured in the ear canal. The lower level probe tone indicates that some of the energy of the probe tone is flowing out of the ear canal and into the middle ear. A higher level probe tone indicates that the energy of the probe tone is not flowing into the middle ear cavity, but is reflected back from the TM, or eardrum, or tympanic membrane, into the ear canal. So admittance of the middle ear in adults, it would be greater than or equal to, well, in adults greater than or equal to 18 years, we would expect to see admittance of 0.3 to 1.7 millimos at the peak. And then equivalent volume of the ear canal in adults is 0.6 to 2.0 milliliters. So if we saw in our data, in our test results, that the equivalent volume of the ear canal was greater than 2.0 milliliters, we might have the presence of a perforation or a hole or maybe a pressure equalization tube inside the eardrum. So if you see a large ear canal volume, it might be that the equipment is actually measuring the volume not only of the external ear canal but also of the middle ear, because there is a hole in the eardrum. If we saw lower than normal volume for the ear canal, that could mean that there's some foreign substance or some debris inside the ear canal, such as impacted cerumen. Note, the higher than normal ear canal volume is consistent with a TM perforation. Smaller than normal ear canal volume is consistent with the presence of a significant amount of cerumen or other object inside the TM. Let's talk about some middle ear conditions. Otosclerosis is fixation of the stapes in the oval window. There could be some a little growth around the stapes that freezes the stapes footplate in the oval window. This greatly decreases the amount of sound that will, or sound vibrations that will be allowed to be transferred into the inner ear. When that happens, we can expect a hearing loss. We have a condition called disarticulation or disruption of the ossicular chain. This means that those three bones, the malleus, incus, and stapes, somewhere along the line are broken apart. That may happen when somebody sustains a blow to the head, or if they were in a car accident, etc., where they hit their head. Otitis media. Otitis is infection of the ear, and media is the middle part, so that's a middle ear infection. Next we have otitis media with effusion. So that's when fluid is in the middle ear. So there's an infection in the middle ear, and we have fluid in the middle ear, most likely due to the presence of negative pressure in the middle ear, which is secondary to a faulty or a poorly functioning eustachian tube. When the eustachian tube is poorly functioning, we can actually obtain a negative pressure in the middle ear, and that can cause a situation where the mucus lining in the middle ear will start to secrete all this liquid, all this fluid, and you can look at an ear that has otitis media with effusion, and you can actually see the fluid. You can actually see a fluid line, or sometimes you can see air bubbles in the fluid looking through the TM. A highly mobile tympanic membrane can be due to disarticulation of the ossicular chain, or it could be due to a thin tympanic membrane as a result of a history of middle ear infections. Now, how do those two things relate? Well, you can have a history of middle ear infections, you can have a history of the fluid building up to such a point that it bursts a hole through, it bursts through the tympanic membrane and causes a hole. When the hole in the TM, or the perforation in the TM, heals, the membrane now is a little thin in the site where you had the perforation. And that can result in a highly mobile tympanic membrane. Tympanic membrane perforation is also called a hole, is a hole in the eardrum. A PE tube, or pressure equalization tube, is when there's a hole placed in the eardrum and a little, I don't know what it is, it's plastic or nylon, I think it's nylon. It looks like a very tiny nylon tube that's gently placed in a little tiny slit that the surgeon makes with the scalpel. And that is installed whenever there is a strong history of chronic middle ear infections with effusion. And this is to help the fluid drain out of the middle ear. Having a middle ear full of fluid is not a healthy condition. PE tube, oh, we just talked about that. Okay, and then impacted cerumen. A Q-tip usage may create impacted cerumen, and it may cause an earplug to form in the ear canal. Okay, according to Janet Shanks in her paper from 1984, the differential diagnosis of most middle ear pathologies is not possible based on an analysis of tympanometry alone. So, if we see an abnormality on the tympanogram, that's not enough to help us understand what the exact pathology is. By the same token, if we have a normal tympanogram, that's not enough to tell us that there are no problems in the middle ear, actually, or in the auditory system. So we have different types of tympanograms. We have a normal tympanogram, which we could find when we have normal middle ear function and no air-bone gaps. Notice we're looking at the air-bone gaps on the audiogram, and we're looking at the tympanogram. Or this could be a sign of otosclerosis or disarticulation of the ossicular chain when you have an air-bone gap. So if you have a normal tympanogram, look at the pure tone thresholds, look at the bone conduction thresholds, the air conduction thresholds, and look for that air-bone gap. If you see the air-bone gap, then you decide, wow, okay, maybe we have the presence of otosclerosis or a disarticulation of the ossicular chain. A shallow tympanogram, we would expect an air-bone gap most likely, and reduced movement of the tympanic membrane. This could be secondary to, again, otosclerosis or otitis media with effusion. High admittance on the tympanogram, so very, very tall peak, represents a highly mobile tympanic membrane or disarticulation of the ossicular chain or a thin TM. So a highly mobile TM, is either the result of disarticulation of the ossicular chain or a thinned out tympanic membrane, and we would expect to see an air-bone gap. A flat tympanogram can mean the presence of, or can be secondary to the presence of otitis media with effusion, and with normal ear canal volume and air-bone gaps present on the audiogram. Or it could be from perforation of the tympanic membrane or the presence of a PE tube, and you would see larger than normal ear canal volume and no air-bone gaps. Or a flat tympanogram could be the sign of impacted cerumen when you have smaller than normal ear canal volume, and perhaps air-bone gaps will be present on the tympanogram, on the audiogram. And then negative pressure, a negative pressure peak on the tympanogram should resolve when the eustachian tube is opened. If not, then fluid in the middle ear may build up. So here's a figure from Kramer, figure 711, and here's some of the types of tympanograms we could see. Notice that a shallow tympanogram is called a type A tympanogram, and a flat tympanogram is called a type B tympanogram, and a type C tympanogram has negative pressure that may be due to eustachian tube dysfunction. And then off to the right we have a couple of type A's. You have a type A sub D and a type A sub double D, and that's related to tympanograms with high admittance. So these are the different types of tympanograms that you can see. And then also you can see a normal tympanogram. Okay, acoustic reflex thresholds. This is a test usually performed right after tympanometry, and this test is a measure of the integrity of the neural pathways going from the eighth nerve as it leaves the cochlea. So see, it says IE here, inner ear. Eighth nerve, the signal will go up to the ventral cochlear nucleus in the auditory brainstem, and then signals will be delivered to the superior olivary complex in the brainstem, and contralaterally to the other side, the other superior olivary complex. Notice that we have two ears here. We also have two sets of ventral cochlear nuclei, and we also have two superior olivary complexes. Okay, and notice the pathways. We have ipsilateral pathways, which means pathways on the same side of the ear, or we have pathways that go to the opposite side. So when we play a tone, if everything is healthy and the tone is at a high enough level, the signal will be delivered through the eighth nerve up to the ventral cochlear nucleus. It will be delivered to the superior olivary complex, and then the signal will go down through the efferent pathways. These are afferent pathways going up, right? These are efferent pathways, and then it communicates with the facial nucleus, and then it sends the signal to the seventh nerve, or the facial nerve, that is connected to the stapedius muscle, which is connected to the stapes. When that happens, so when this signal makes this goes through this path, the stapedius muscle will contract. If the stapedius muscle contracts, it's hanging on to or attached to the stapes. It pulls on that and stiffens up the whole articular chain if everything is healthy. When that happens, then the tympanic membrane will also stiffen up. When that happens, the probe tone in the ear will decrease in level at the eardrum, and we'll see, and then from that change in probe tone, we'll infer from that a change in admittance. So the result of the activation of the acoustic reflex pathway is a decrease in admittance. And we can see this by putting the probe tone in this ear and putting something called a reflex eliciting tone in the ear at the same time. So imagine the 226 hertz probe tone, and then we have this another tone that's the reflex eliciting tone, presented at a relatively high level, can elicit this response, and that will cause a change in admittance or a change in the flow of energy. And from that, we can infer something about the neural pathways going from the cochlea through the eighth nerve, up through the brainstem, down the brainstem, and to the stapes, okay, to the facial nerve. So from the eighth nerve through the auditory brainstem pathways to the facial nerve. So we're going to infer from that measure of the acoustic reflex threshold, actually, and we'll get more into that later. We'll infer the neural integrity of the auditory system. Okay, the reflex eliciting tone is 500, 1000, or 2000 hertz. These are all pure tones. A single pressure is used, is presented or placed inside the internal, or rather the external ear canal, usually the peak pressure from the tympanogram. Ipsilateral acoustic reflexes, or IPSI, reflex eliciting tone is delivered to the same ear where admittance is being measured. So for ipsilateral acoustic reflex measurements, we have the probe tone and the reflex eliciting tone in the same ear. Contralateral acoustic reflex measurements, that's when the probe tone is one ear and the reflex eliciting tone is presented to the opposite ear from where admittance is being measured. The probe tone is usually, again, 85 dB SPL and 226 hertz, and it's used to track admittance during the presentation of the reflex eliciting tone. So, again, the picture is we're going to pump some pressure in the ear canal or take some pressure out, which will be at the same where the peak admittance is on the tympanogram, wherever that pressure is, that's the pressure we're going to utilize during the collection of the acoustic reflex threshold. The pressure now is not going to change. That's fixed during the test. We have a probe tone delivered into the ear canal. We're going to monitor the level of the probe tone as we introduce the reflex eliciting tone. And we're going to look for a change in admittance. When the level of the reflex eliciting tone is too low to elicit a response, there will be no change in measurable admittance. When the level of the reflex eliciting tone is high enough to elicit a response, the admittance will decrease during the presentation of the reflex eliciting tone. Acoustic reflex threshold is the lowest level of the reflex eliciting tone in dBHL that produces a repeatable admittance change of at least 0.02 millimoles or 0.02 milliliters. So this is from figure 713 of the Kramer text. And in this diagram, you can see the y-axis is admittance, and the x-axis is actually time, though we don't have the time labeled here. So we're going to look at the change in admittance as we present the reflex eliciting tone. So when we present the reflex eliciting tone at 80 dB, it should say HL, there's no change over time in admittance. Okay, when we present the tone at 85 dB HL, we see that admittance changes a little bit. But does it meet our criteria? Our criteria is 0.02 millimoles or milliliters, and it didn't reach the criteria. Next test run. So this is without the tone being presented. Now the probe tone is still on, but the reflex eliciting tone goes on now, and all of a sudden we see this nice decrease in admittance. Does it meet our criteria of 0.02? Yes, it does. It's 0.04. So, and again, so what happens is we present the probe tone, we're measuring admittance, and then we present the reflex eliciting tone. That goes through the cochlea, it goes up the 8th nerve, up the pathways in the auditory brainstem, and then the signal is sent down to the 7th nerve, which stimulates the stapedius muscle, which grabs the ossicular chain via the stapes and stiffens the tympanic membrane. When the tympanic membrane is stiffened, then admittance is decreased, and that is inferred from an increase in the probe tone measured in the middle ear. Now, just to be thorough, this actually could have been due, at 90, this could have been due to some sort of artifact. We'll talk more about that in a second. So we want to make sure of our measures, so we're going to increase the tone to 95 dB HL. Now look at this nice response here. This is great. So we have a larger change in admittance or decrease in admittance. And now we're going to go back down to 90 to confirm that this is repeatable. And we see this nice acoustic reflex response. It meets our criteria, so we're going to say, well, since this is repeatable, and all this indicates that this looks like the real thing. Now, we have to be careful, because swallowing by the patient, or if the patient clenches his or her teeth, that can also change, cause a change in admittance. And that's not a reflection, of course, of the acoustic reflex pathways or the acoustic reflex arc. So just to watch for that, that's why we need to repeat our measurement here, looking at the reflex at 90 dB HL. We have to do that twice. Okay, acoustic reflex threshold. To increase confidence in establishing the acoustic reflex threshold, it is recommended that testing be conducted 5 dB higher than the pure tone threshold for the test frequency. The reflex eliciting tones above 105 dB HL may cause tinnitus or tinnitus and are therefore not recommended routinely. Movement artifacts such as swallowing or teeth clenching may interfere with the acoustic reflex threshold measurements. Some general rules for interpretation. The ear with the probe tone must not have any outer or middle ear pathology. If there's a big wax plug in the in the ear canal, we cannot measure the acoustic reflex threshold. If there's a bunch of fluid in the middle ear, most likely we're not going to measure the acoustic reflex threshold at all. Okay? And then the ear with the reflex eliciting tone must receive a tone that is high enough, at a high enough level, meaning above the threshold. So we can look at the audiogram and we can answer the question, is this tone audible for this patient? And if it's audible, then we're going to trust that the signal, if everything's functioning normally, the signal will go up the brainstem response. The neural pathway must be adequate to activate the contraction of the stapedius muscle. And then here's some points from table 7.4 in the Kramer text, summary of the most expected acoustic reflex thresholds for different types of pathologies. If you get a reflex in the normal range, there should not be any outer ear or middle ear pathology in the probe ear. And expect an acoustic reflex for most cochlear losses, meaning that the site of lesion is in the cochlea, and you would see some sort of hearing loss. For pure tones, a normal reflex does not rule out cochlear hearing loss, meaning damage in the sensory organ or damage in the cochlea. The level of the acoustic reflex threshold does not define the degree of hearing loss. If the acoustic reflex threshold is absent in the presence of a normal pure tone threshold or elevated pure tone thresholds less than or greater than 70 dBHL, this may be a sign of a possible eighth nerve pathology, such as an acoustic neuroma, also known as a vestibular schwannoma. If the acoustic reflex threshold is greater than the 90th percentile in the distribution of the norms, this may be a sign of eighth nerve pathology. Okay, and that's our lecture for now on tympanometry and acoustic reflex thresholds.